In Chapter 15, we study other classes of equilibria, and in particular, we're going to be focusing on equilibria associated with precipitation, that is forming a solid, and dissolution, that's things dissolving. So way back in Chemistry 161, when we were studying precipitation reactions, we noted that some ionic compounds are not very soluble in aqueous solution. And a classic example of these are a large number of metal hydroxides are not very soluble in aqueous solution. So what happens when these guys are brought into contact with water is an equilibrium is established. It favors the left-hand side. So you get mostly solid and then a little bit of the ions. And in the case of magnesium hydroxide, what you're going to get is you're going to get for every mole of magnesium hydroxide, you'll get 1 mole of magnesium ions and 2 moles of hydroxide ions. So this is an equilibrium, and like I said, for a sparingly soluble compound, it'll favor the left-hand side. So the equilibrium constant for a solid ionic compound in equilibrium with its solution is called the solubility product constant. Most people call it the Ksp. And because we don't include solids in the expression for an equilibrium constant, remember equilibrium constant is just products over reactants, and then it just becomes the product of the ion concentrations, and each of those ion concentrations is raised to the power of its stoichiometric coefficient. The key thing to recognize though is that the bigger that the Ksp is for a compound, the greater its solubility. So there's whole big tables of KSPs. They're given in the appendix of your book, and they're given in ALEX as well. So if you need those, you can always look them up. So related to the concept of KSP is the idea of a compound's molar solubility. And the molar solubility is the number of moles of solid in 1 liter of a saturated solution. So pretty easy to make a saturated solution. You take some water, and then you dump in your compound until you have a nice little pile of solid at the bottom, and you're completely convinced that no more can be dissolved. And then you filter off the liquid that's above that solid, and that's going to be your saturated solution. Okay, so that's basically how we always make a saturated solution. Now the cool thing about the Ksp and the molar solubility is if you have one, you can always calculate the other. Now, it's not sort of like super simple. There isn't a formula for doing it. You have to do a little bit of work, but you can probably see that this is possible. So here's an example again of our magnesium hydroxide solid in equilibrium with the magnesium ion and the hydroxide ion. And what we would know is that this is really sparingly soluble, so it's going to have a small Ksp, which it does, 5.6 by 10 to the minus 12. But we know that for every x moles of this, I'm going to get 2x moles of this, right? So we're getting that because of the coefficients here. So we really only need to know the concentration of one thing in order to figure out the Ksp. So how many moles of this guy can dissolve in 1 liter? How might we go about solving that? We've got the Ksp here. Let's have a look. All right. So the number of moles of magnesium hydroxide that would be in 1 liter of solution, of a saturated solution, if we let that just be X, right? X moles of this stuff dissolves. And then the concentration of magnesium would be X, and the concentration of hydroxide ion would be 2X. So and now I can go through, and I know that Ksp is going to be the concentration of magnesium ions multiplied by the concentration of hydroxide ions. So that's going to be x times by 2x squared. So 2x squared gives me 4x squared multiplied by x gives me 4x cubed. You always got to make sure you don't do any sort of like errors with the algebra in here. Classic mistake is 2x squared equals 4x squared. Sometimes people will do that it equals 2x squared because they'll forget to square both parts of that expression. So just be aware for making sort of like minor slips like that and getting things wrong. Okay, so I've got my expression for Ksp in terms of x now. Ksp equals 4x cubed. So divide by 4 and take the cube root is going to give me x. So yeah, looks like I'm good to go, right? Now, of course, you can always use the solver. You'll find the cube root function under the math menu on your calculator, or you can always do, you know, to the power of a third and do it that way if you can't be bothered finding out where the cube root is. So once I do that, I would expect it to be a pretty small number, right? Because the Ksp is like 10 to the minus 12. When I do get the molar solubility, it's 1.1 by 10 to the minus 4. So that's a small number consistent with my tiny little Ksp. Okay, so I said that we can't really have a standard formula relating the Ksp and the molar solubility, and the reason is because it's going to be the relationship between those two things is going to be dependent upon the nature of the subscripts and the ratio of the positive ions to negative ions. So you'll see that in this example here. So phosphates are another example of ionic compounds that are well known for their insolubility. And so we're going to calculate the molar solubility of calcium phosphate. It has a Ksp of 2.1 by 10 to the minus 33. So that's really, really, really small, right? So when calcium phosphate dissolves, we get 3 moles of calcium ions and we get 2 moles of phosphate ions. So if X moles of calcium phosphate dissolve, we would get 3x moles of calcium ions and 2x moles of phosphate ions. So here's the Ksp expression. We have to take the cube of the calcium ion concentration and multiply that by the square of the phosphate ion concentration. We don't include the solid in our equilibrium expressions. So if we have X moles of calcium phosphate in a liter of saturated solution, then our Ksp would be 3x cubed multiplied by 2x squared. And now I've just got to be really careful not to make an error with my math. Or you could use the solver. So that this is going to equate out to 27x cubed times 4x squared, which gives 108x to the 5. Now before we had Ksp equaled 4x cubed. You see, you can't use the same relationship every time because it depends on the ratio of the cations to the anions, how that algebra is going to work out. So yeah, you have to kind of work through it. Okay, so what have I got to do to get X? It's going to be Ksp on 108 to the 5th root. There it is there. And then when I solve that, it's an itty bitty number. Now calcium phosphate has a smaller molar solubility than magnesium hydroxide, which we would expect because the Ksp for calcium phosphate is a lot smaller than what it is for magnesium hydroxide. Okay, it's not very soluble at all, calcium phosphate. So now we're going to have a look at an example of a problem where we have what's called a common ion present. And we're going to see the effect of the common ion. So it says, do you expect the solubility of barium sulfate to be less or more in seawater? And it says the concentration of sulfate ion in seawater is 2.8 grams per liter. And they're like, ugh. Why the heck didn't they give me moles per liter? All right. And then it says, confirm your answer numerically. So let's go with the do you expect? So what we're saying is if I had fresh water and I tried to dissolve some barium sulfate, what would happen is it would come into equilibrium with barium ions and sulfate ions. Now, what's the difference between freshwater and seawater? Well, the seawater has a much higher concentration of sulfate ions. So what that's going to do is push this equilibrium to the left. So my expectation is that according to Le Chatelier's principle, when I increase the sulfate ion concentration, I'm going to decrease the solubility of barium sulfate, and I would expect that barium sulfate will be less soluble in seawater. And this is called the common ion effect. And what it's saying is if you had a source of one of the ions that's on the right-hand side of the equilibrium, so maybe you added some barium chloride or maybe you added some sodium sulfate, you're going to reduce the solubility of this guy because it will push the equilibrium to the left. So let's go through and figure out what the solubility of barium sulfate would be in fresh water. So when this system comes to equilibrium, we would have X moles of barium and X moles per liter of sulfate, because, you know, for every X of this that dissolves, we get 1x of each of these things, right? So that's easy. So Ksp is just going to be the concentration of barium multiplied by the concentration of sulfate, and that's just going to be x squared. I looked my Ksp up in the back of my book, and it was 9.1 by 10 to the minus 1. So x equals the square root of Ksp, and that's the square root of that number there. So it's really small, right, in the fresh water. So that's the fresh water. Okay. All right, now what we're expecting is a smaller value in the salt water. So the first thing we're going to have to do is deal with this nasty 2.8 grams per liter. We need to turn it into moles per liter because we can only use KSPs for when we're doing moles per liter. So 2.8 grams per liter, I need to turn my grams into moles. 1 mole of sulfate, we've got a sulfur and 4 oxygens there. So my 2.8 grams per liter equates to 0.029 moles per liter of the sulfate anion. So when I take my barium sulfate and put it into water and allow it to come into equilibrium, for every X moles of barium sulfate that dissolve, I'll get X moles of barium ions. Now the concentration of my sulfate ions, it started at 0.029, and then I'm going to add a little more. Now you want to remember that even when it was fresh water, the little bit extra that I was adding was just 9.54 by 10 to the minus 6. So I'm just not worried about the little bit extra that's going to come along from the barium sulfate dissolving. I've just left my sulfate ion concentration at equilibrium as being just 0.029. You could expand that out and you know, do like that if you really wanted to and get an exact answer. It's really not going to help you. Okay. All right. So what's my Ksp? It's the concentration of my barium ions multiplied by the concentration of my sulfate ions, which is going to be X times 0.029. So now I've got to solve for X. So I've got to divide both sides by 0.029, and there I go. So it's a much smaller number, right? 3.14 by 10 to the minus 9. It's like 1,000 times smaller, all right? So in pure water, the concentration of barium sulfate will be 9.54 by 10 to the minus 6 moles per liter. In the seawater, it's like 1,000 times less. 3.14 by 10 to the minus 9 moles per liter. So you can kind of see the effect is pretty dramatic. It's Le Chatelier's principle in effect. It's a special case of Le Chatelier's principle called the common ion effect. You add a common ion and it pushes the equilibrium to the left. You can also see that, you know, adding in this little X in here, I wouldn't have got any different if I did that like that. I guarantee you if I'd used the solver to solve that to 3 significant figures, this would have been, or this number here, sorry, would have been the same one. Okay. So they're 2 really stereotypical problems for Ksp. One is calculating the molar solubility of a substance given its Ksp. The other calculating the molar solubility of a substance in the presence of a common ion. The next type of problem that we're going to look at is a little bit more elaborate. These are problems not about dissolving stuff, but more about precipitating stuff. Okay, so we had previously stated that if Q is bigger than K, then the equilibrium will spontaneously move to the left. And in the case of when we're talking about the solubility of an ionic compound, what that means is a precipitate forming. So if we do something to our equilibrium system to make it such that Q is bigger than Ksp, then we're going to form a solid. And that's going to cause the concentration of our ions to decrease. And that can be useful. Or sometimes it can be annoying that that's happening. So that's what we're going to look at in the next sort of little example problem. So here we have a sample of lead chloride. It has a pretty small Ksp, 1.6 by 10 to the minus 5. It's sparingly soluble in water. What we're going to do now is we're going to add 350 mils of a 0.15 mole per liter solution of lead nitrate. So you're automatically thinking, aha, we're adding a source of lead ions. This is an example of the common ion effect, right? It's going to reduce our solubility of our lead chloride by doing this because we're adding a common ion, right? So this is if 350 mils of 0.15 mole per liter lead nitrate solution is combined with 150 mils of sodium chloride. Okay, so let me thinking about this. What we're doing here is that's going to be a source of lead ions, and this is going to be a source of chloride ions, right? So that's what's happening here. Now it's going to get nasty because whenever I'm mixing two solutions together, a dilution is occurring, right? So what's happening? Lead chloride is sparingly soluble. That's just a little bit of information they're giving you, the Ksp. Will a precipitate form if 350 mils of 0.15 moles per liter lead 2 nitrate is combined with 150 mils of 0.1 mole per liter sodium chloride? So basically you're combining a source of lead ions with a source of chloride ions, and you're trying to figure out if a solid will form. So what you got to do is figure out the concentration of your lead, figure out your concentration of your chloride, and then calculate Q for this reaction, which will just be my concentration of my lead ions multiplied by the concentration of my chloride ions, and then compare that to K, right? Is it bigger if it's smaller? And if it's bigger than K, then that equilibrium is going to shift to the left and a precipitate will form. So I'm doing C1V1 equals C2V2 type calculations to calculate my concentration of my lead. So C2 equals C1V1 on V2. So my concentration of my lead after the dilution is going to be equal to my initial concentration, 0.15 molar, multiplied by my initial volume, 350 mils, divided by my final volume, 350 plus 150 mils, or 500 mils. Mils cancels out, leaves me with moles per liter. So I get my lead ion concentration after the dilution. Now I've got to go through calculate my chloride ion concentration after the dilution. I began with 0.1 mole per liter sodium chloride. So that's my concentration of chloride to begin with. That's my C1. I used 150 milliliters of it. That's my V1. And then again, after the dilution, because we're combining 350 and 150 mils, I have 500 mils total. Do the math on that, and I've got 0.03 molar chloride ion. So now I go ahead and I calculate my Q. Q equals my lead ion concentration multiplied by my chloride ion concentration squared, because I have two of those guys there. Do the math on that. 9.45 by 10 to the minus 5. And then I have to compare that to my K. And what I decide is that Q is bigger than K. Whenever Q is bigger than K, the equilibrium moves to the left, which in this case means a precipitate will form. So, there's a lot of kind of creative thinking as to how to solve that problem. And the key thing is recognizing whenever you're combining more than one solution together, you're frequently going to need to do a dilution type problem. Okay, so that's one sort of example of where we are predicting if a precipitate will form when we're mixing two solutions together. Each of them contains a common ion. One common ion from one thing, one common ion from the other. The more complex problem is where we use our understanding of solution equilibria to selectively remove one component from a multi-component system. So we previously were looking at lead chloride, and we saw that it is sparingly soluble and its Ksp is about 1.6 by 10 to the minus 5. If we look at lead fluoride, we'll see that or lead 2 fluoride, I should say more exactly or more correctly, its Ksp is a lot smaller, which is actually typical for fluorides. Fluorides are often quite insoluble. 3.2 by 10 to the minus 8 for its Ksp. So, it's about 1,000 times smaller. So if I had a mixture of chloride ions and fluoride ions that had the same concentration, and then I add lead to it, what I would expect to see is that lead fluoride will get precipitated before lead 2 chloride, because lead 2 fluoride is just so much less soluble. This could be a mechanism for removing fluoride ions from a mixture of fluoride and chloride ions. We could selectively precipitate the fluoride ions, which is kind of cool. So here's an example problem of doing that, right? So it says lead chloride gives the Ksp, and lead fluoride, and again gives the Ksp, are both slightly soluble compounds. So they're just giving you the Ksp. Then it says, consider a solution in which the chloride ion concentration equals the fluoride ion concentration, and the concentration of both components is 0.275 moles per liter. What we're going to do now is says, can addition of a solution of lead 2 nitrate, so this is a source of lead 2 plus ions, be used to reduce the fluoride ion concentration to less than 2.75 by 10 to the minus 4 moles per liter without precipitating any chloride. Now this seems like a question that, this seems like a sort of classic sort of question that might be asked of a chemical engineer. So this is quite interesting. So here are our two equilibria. Lead chloride is in equilibrium with lead 2 ions and 2 chloride ions, and we've got our Ksp, and then we've got lead fluoride in equilibrium with lead 2 plus ions and fluoride ions, and again we've got our Ksp. So the first thing I'm going to ask myself is, what is the maximum concentration of lead that I can have without precipitating any chloride, right? So I always want to begin by doing that. Calculate what is the maximum concentration of lead that can be present without precipitating your more soluble component, okay? Without precipitating your more soluble component. So let's see what we've got here. So Ksp for the lead chloride is 1.6 by 10 to the minus 5, and we're going to try and that's equal to the lead ion concentration multiplied by the chloride ion concentration squared. And what we're going to try and do is calculate the lead ion concentration. So Ksp on the chloride ion concentration squared will give us the lead ion concentration. So 1.6 by 10 to the minus 5 over 0.275 squared. I'm just getting that from there. That's a fixed number. So that gives me 2.11 by 10 to the minus 4 moles per liter of lead 2 plus. So that's the maximum amount of lead that I can add before I begin precipitating lead chloride, right? Okay, so now my question becomes, what is the concentration of fluoride ion at this maximum lead concentration, and is that less than 2.75 by 10 to the minus 4? So Ksp for the lead fluoride is the lead ion concentration multiplied by the fluoride ion concentration squared, and I'm told that that equals 3.2 by 10 to the minus 8. So now if I just do the square root of Ksp on the lead ion concentration, I will get the fluoride ion concentration, which is the expression that I've got written here. So I go through and I do the math for that, and it turns out that I can't, right? That as soon as I keep adding lead, but at the point when I begin precipitating lead chloride, my fluoride ion concentration is only dropped to 0.012 moles per liter. I mean, I've got rid of a lot of the fluoride at that point, but I haven't dropped it down to the desired amount. So all of these kinds of problems with selective precipitation are done in a similar manner. So begin by doing the math for the more soluble compound and calculate the maximum concentration that can be tolerated without precipitating that more soluble compound, and then feed that information into the part of the problem dealing with the less soluble compound. You always know what one's more soluble and what one's less soluble by looking at the KSPs. Okay, so